In section 7.5, we're going to solve some more trigonometric equations, ones where we actually have to convert some of our trig functions into something else in order to solve it. Think about solving equations. We can only solve an equation if everything has the same variables. So if you have an x and a y in an equation, you can't solve it and get a numerical value. The same is kind of true of trigonometric equations. We can't have different trigonometric equations together in order to solve this. So I'm going to have to do a little converting. Well, one of the things I recall is that cosine squared theta is actually the same thing as 1 minus sine squared theta. So if I convert that, now I'm working with an equation that only has one trig function in it. This is actually going to be a quadratic equation, similar to one we saw in the last section. I'm going to go and first write this in descending order of powers. So I'm going to move the negative 2 sine squared theta to the other side. It becomes positive. Sine theta stays where it's at, so it still says plus sine theta. But then I'm going to subtract the 2 from the 1 and get negative 1. So in this quadratic equation, you have two choices. You can either factor it the long way by factor by grouping, or you can just graph it in your calculator and find where it hits the x-axis. If you do that, you're going to find that it hits the x-axis at a half and at negative 1. But that's not really the equation, so I'm pretending, that this is the equation I'm solving. Well, this isn't really what I'm solving. What I'm really solving is sine theta equals 1/2, and sine theta equals negative 1. Let me start with the easy one, which is sine theta equals negative 1. On the unit circle, there is only one location where sine is negative 1, and that is at 270 degrees, which is 3 pi over 2. But because we want to find all the solutions, remember that we tack on that 2 pi k at the end. The other equation, sine theta equals 1/2, we've run across this several times now. 30 degrees is the one whose sine is 1/2. Well, 30 degrees is pi over 6, and we add the 2 pi k. But there's another location that if I take its sine, it gives me positive 1/2, and it's in quadrant 2. It's 150 degrees, also known as 5 pi over 6. And those are my solutions. Let's look at a different problem where we're going to factor again in a way that we factored in the last section. I want to solve 2 theta minus cosine theta equals 0. Well, we know that sine 2 theta by the double angle theorem is the same as 2 times the sine of theta times the cosine of theta. Now I have an expression that has two terms with a common factor. So how about I factor out that common factor of cosine theta? And I'm left with 2 sine theta minus 1. Now I can solve this using the zero product property. And I kind of feel like this is the exact same problem from the last section, except that instead we just told you what sine 2 theta was, and it probably is. So where is the cosine of theta equal to 0? Well, if you look at the unit circle, you find that it hits 0 at pi over 2, which is 90 degrees, and it hits again at 270 degrees, which is 3 pi over 2. And don't forget your 2 pi k's. This one, when I solve, I'm going to get sine theta is equal to 1/2, and this is the one we keep coming up with. So by now I hope you've got it memorized. The two answers where sine is positive 1/2 is going to be pi over 6 and 5 pi over 6. In this problem, solve 2 sine 3 theta minus 1 equals 0. Don't worry about this sine 3 theta right now. Let's do this. Let's pretend like this says 2x minus 1 equals 0, so you know that x is 1/2. Well, instead of x equaling 1/2, sine of 3 theta is going to equal 1/2. Well, when we go to solve this problem, we take the inverse sine of the other side. And since we've run across this problem several times, we already know that the inverse sine of 1/2 is going to be pi over 6 plus 2 pi k. And the other answer is going to be 5 pi over 6 plus 2 pi k. I should make that look like a k. Well, all I have to do now to solve for theta is multiply the other side by the reciprocal of 3. The reciprocal of 3 is 1/3. So I'm going to change this. Theta is equal to pi over 18 plus 2 pi k. Notice that I only multiply the pi over 6 by the 3. And the other one is going to be 5 pi over 18 plus 2 pi k. So I do the problem like I normally do it. The only thing I have to do at the very end of the problem is multiply by the reciprocal 3, or divide everything by 3. The last problem we're going to work on, the square root of 3 tangent theta over 2 minus 1 equals 0. Again, pretend for a moment like that's x. Let me change colors here. So if I solve this for x, I find out that x is 1 over the square root of 3, which is square root of 3 over 3, by the way. That means it's one of our special angles. Well, this is really going to be tangent theta over 2 is equal to square root of 3 over 3. Remember that tangent, we're only going to get one answer instead of writing 2, because tangent's period was only 1 pi, and the answers that are both positive or both negative are already 180 degrees away from each other. So when you do the inverse tangent of the square root of 3 over 3, if you do that in degrees and then change it back into radians, you're going to find out it's 30 degrees, which is pi over 6. So let's move this up. Theta over 2 is going to equal pi over 6 plus pi k. So all I have to do to finish solving for theta is to multiply the other side by 2. Well, I get 2 pi over 6. 2 pi over 6 reduces to pi over 3. And those are some more trig equations, a little bit more difficult than the ones in the previous section, but not too bad.